Right. So now we're going to change gears a little bit, and the next several talks will be focused on debris flows. And up first, we have Ben Leshchinsky from Oregon State University.
All right. Hi, everybody. Thanks for having me here today. I'm going to preface this by saying that a lot of this is preliminary, ongoing work. You know, I wish I had all the answers today, but I have a feeling it's going to take a little while. But we'll talk about what we've seen. And I'd also like to say a lot of this credit goes to a big group of people. I'm just the messenger here, especially some fantastic grad students who've just really been engaged, wanting to get out in the field and get some data. So with that, we'll get into this. So we have a project that's 1 year in with the Oregon Department of Transportation as well as the Forest Service, who's facilitating land access to constrain some landslide hazards we see following wildfires. There's a bunch of people on the team. I note some of them here, but there's one missing, you. We're an open tent. We're looking for collaboration, whether it's data sharing, ideas. I'm just a lowly geotechnical engineer. I don't know too much about all these other processes, these interesting things I've seen today. So I welcome anybody to just come have a chat, teach me something. I'd love to learn. We welcome you. So some things we're trying to do, and we're in the process of doing, is cataloging some data associated with post-fire mass wasting, whether that's the form of shallow landslides, debris flows, whatever events we can find, particularly that we can associate with some sort of precipitation event, or snowmelt for that matter. Of course, the focus of this, considering that it is funded by the Department of Transportation, is that what are the impacts of these events to our highway transportation system? You know, if anybody's driven I-84 in the last couple of years, you might have noticed that there's a lot of cleaning of debris going on, right? We are seeing a lot of debris flow impacts there, and the big question, open question at that, is what's going to happen in the 2020 SCARs? So some things we're trying to do, there's lots of facets to this project, but we're trying to advance at least some of our understandings of some of the controls we've seen, whether they be mechanical, hydrological, climatic, whatever they might be, on what controls what we see in terms of these landslides and potential debris flow events throughout Oregon. And this includes monitoring, modeling, mapping, all the M words here to inform some of our planners and what we plan to do going ahead. So some of the facets of the project so far, and it's really just kind of getting off the ground. There's some field work, the best part, always the best part. We've installed a series of monitoring stations. We'll talk about that a little bit, basically looking at, of course, climatic variables and controls, as well as some of the soil variables that we've observed. There's some lab work. You know, one thing I'll talk about quite a bit is roots, and there's so much to learn there from the bio side, and I welcome that. But we've been extracting roots and testing their tensile strength at a variety of sizes and trying to understand how post-fire those values change. Here's a hint, changes a lot. Some office work, of course, particularly when it's too rainy and snowy to get outside, although I love that too. Some modeling, which is just getting off the ground, that's very preliminary, and some mapping efforts, which will actually commence today, this afternoon. Yeah, no time wasted. What we need, and what there's a lack of, and what I suppose you'll probably hear in the great talks following this, are that, you know, there's kind of a lack of inventoried landslides and debris flows following these events. But there's more data needed, and particularly more data that we can associate with a climatic control, snowmelt, rainfall. So the monitoring stations, we'll get into it. We have several monitoring stations, 4 installed so far. I wish it was more. We have 2 more set to go. But each monitoring station, or MET station, includes 3 volumetric water content sensors placed at depths, pore pressure sensor, basically a shallow well that we can drill into the ground, rainfall, and all this data is collected at a 5-minute interval, temperature, relative humidity, and it's all telemetered online so we can monitor it in real time. We've tried to place them in steep, landslide-prone terrain. I feel sore just thinking about placing some of these systems out there. It was a lot of fun, but I was pretty tired. I'm getting old. And we consider that these sites at least might serve as one of several proxies for what the disturbance might be to cause some of these shallow landslides and debris flow events that we see at these sites. But of course, proximity is the key here, and I suppose something you'll hear a lot about this afternoon. Holiday Farm, one of our sites. We have a few sites we're looking at. Holiday Farm represents basically a little more than 2 years after the fire. We've chosen 2 MET stations there, placed not too far from each other, both in a burned and relatively unburned site. They're both on hollows, 33 degrees. I love the previous talking about the heterogeneity, the variability you see over these scales. You know, not far, these sites aren't far from each other, but they have pretty different soil conditions. And this is just the reality. One of the big challenges, actually, in placing monitoring stations, comparing, contrasting, what's your control in the end? Well, for that, whatever it's worth, we have these two sites, and what we wanted to do is at least compare and contrast precipitation data, soil water response. So here's some pictures of the sites. You can see, pretty steep. You can see why I was sore. Oh man, I'm still sore from that. Here's Francis from the USGS helping with some hydrologic data, hiding behind a bush. Here are the great grad students, some of them installing the sensors out here in the site. This is our burn site. So what we can get from this, and it's really just something we're still looking at, we're just diving into it, it's almost drowning in data for as few stations as we have, is a hydrological time series. So it's busy, so bear with me, but you have these two plots here. Those represent volumetric water contents at varying depths at this burned and unburned site. As expected, we see pretty strong responses to rain events. These are rainfall time series, both cumulative and individual events. Those are the spikes. And of course, we see that there is a response for both sites when we have particularly big rain events. There's a near immediate spike. Of course, the two sites are rather different in terms of texture. So we can see that in terms of the time series of volumetric water content. But in the end, at least we have some data, including precipitation data, and some variability in the site conditions we can use. One interesting thing we've noticed here is that there's continued saturation at bedrock in one of the sites. And the area actually seems like it might be an old scar of a shallow landslide, so we're hoping to see something from that. If you compare the storm events between these, these spikes you see here, there's some short, intense rainstorms that we've seen here. They're not always at the same time, but largely they match. But even for this short distance, you see that there's these kind of microclimatic effects. There's differences. Another confounding variable adds to that heterogeneity. So we can at least take that event data, though. We can take it, look at a variety of durations, 5 minutes to 28 days, or even longer if you want, but the response becomes diffuse. We can use some of our site-measured hydraulic conductivity measurements to consider, okay, how much water can this ground drink up? How fast can it happen? So we have some measurements, and there's, of course, variability here. And what we see, at least, it's a little bit difficult to see, but here's total rainfall, duration. Those lines represent basically the threshold about whether it can absorb the water quickly enough under those conditions or not. And this is where rainfall is happening more quickly than it can actually be absorbed into the ground, but there's a lot of variability there. But what we see, at least for these conditions and all other variables aside, is that we've had some pretty big rain events at Holiday Farm, under very short durations in particular, and in some instances, it exceeds the field capacity. But for the most part, so that would suggest that runoff is a possibility, at least 2 years in. But for the most part, we see that for the longer duration events, that infiltration is very much possible. And this is potentially suggests that infiltration-driven failures, AKA shallow landslides, they can happen. We have limited events observed so far. There might be an observation bias. It'd be great to see more data. But there might be other controls on the delay in these landslide events. So here, I'll get rid of log scales because they make my brain hurt quite a bit. But you see if you go linear scale, total rainfall, here's the event time. In some instances, we're exceeding the capacity by quite a bit, 10 millimeters, for example. So one part of this project is kind of questioning why we see this delayed response. So unfortunately, time travel doesn't exist. So the best we can do is look at Eagle Creek, which burned in 2017. We've installed sensors there as well to look back a little bit further in time. Owing to telemetry issues, we did install 2 sensors, but unfortunately both in burn sites. But that's okay. They still give us things to compare and contrast. One's on a pretty steep hollow, bedrock depth about 180 centimeters. One's on modestly steep divergent terrain with slightly shallower soil depths. I'll also like to note, I'm sure Michael will talk about this later, they're placed pretty close to this pretty amazing debris flow area where there's a deep-seated landslide just pushing material down. So not too far from there, and there's been quite a bit of debris flow activity throughout the gorge, here included. Here we are. This is one of our sites. You can see our diligent grad students just getting roots, installing sensors. It's pretty amazing. I also like to note, despite feeling very cold looking at this photo, how much revegetation is occurring. I mean, it's kind of amazing how this stuff grows back, right? The trees and the vegetation. So here we are installing our instruments. And we can still get this hydrological time series here. So one thing, and as expected, it is much, much wetter than Holiday Farm at this site in the Columbia River Gorge. There's relatively deep soils in some points, and Josh asked a question about burrowing and macropores. There were so many macropores in this place, quite a few. The burrow holes were huge. And it's kind of suggests that, the soils can really drink up water, even under the pretty intense rainfall that you might see in the Columbia River Gorge. What we saw is relatively sustained moisture time series after wet up. And there were some major storm events we had. Early November, right around Thanksgiving, Christmas Day, and we actually had some minor debris flows reported in November. That's what Bill and Nancy mentioned to us. Some of the short duration events we saw at these sites are significant, but note they don't necessarily align, again showing that you might have two different stations not too far away from one another, and you might have relatively different rainfalls, at least the intense events at these sites. Again, we can plot up, based on our hydraulic connectivities at the site, about seeing where capacity might be exceeded. You can see pretty high capacities here. We saw that for at least 5 to 30-minute events, there was numerous times that we actually exceeded the infiltration capacity. And that means that, again, we can have runoff here. But we've also had some for the most part, most of our water can enter the ground, at least for longer duration storms. And it suggests that, again, infiltration-driven failures are possible. This site's had some pretty big debris flow events, including one that had a fatality in 2021, tragically. There are events in 2020, 2021, and 2022, and we'll talk about that a tiny bit. Again, here's some of our short duration total rainfalls for different durations here, and you can see in some of our instances, we're really, really exceeding some of the rainfall here. Here is a picture from Bill and Nancy at Dogami here. You can see they went out on November 7th following some of these big storms, and you can see that the debris had been quickly cleared from one of the culverts right there on the historic highway. So something happened, and we hope we caught something, but one data point is not enough. What's forthcoming? The Forest Service, Cheryl in particular, has been amazing at facilitating some research on these lands. And one thing we've applied to is we wanted another data point. What about recent after a fire? So we applied for permits for Cedar Creek. We got them in November. Unfortunately, owing to my poor timing, happened to have our first snow event, and that site is likely under quite a bit of snow at this point. But we're hoping to get out there in the spring, maybe early summer, considering it's at about 5,500 feet of elevation. And so the site has burned and unburned conditions present, and extensive signs of slope failure. You can see, it's kind of tough to see here, but you can see quite a bit of ravel, scars as well, and down at the base of this, there's actually significant debris flow fans. So our hope is to get our 2 final MET stations out there this coming summertime, and actually hopefully purchase a few more MET stations and get them out. This at least gives us another data point in time. So this is forthcoming. Again, since the grad students on this project are just fantastic, they're really, really awesome, they're eager to get out there. So they were able to get out there, at least collect some roots, and get us data points on what the root strength is. That data is forthcoming. We have to process it at this point. This was like last week. But we're hoping to get some, and you can see, burn and unburn, there's quite a bit of roots in there. All right, so soil and roots. We have a bunch of grab samples, some core samples from the sites, where we can characterize index properties of soil, grain size distributions, strength, the things you might care about when it comes to landsliding. Of course, we've also performed some in situ tests, like mini disc infiltrometers to get those field capacities. We've dug multiple test pits at the sites for installing sensors, but more so, just getting those roots out of the ground and testing them. Root testing has been performed so far on live roots as well as post-fire dead roots to determine loss of strength. And here we are. We'll enter the lab. So what we've done is we've taken these roots into the lab and done tensile testing. I'll talk about that in a bit. And the reason that we've done this is because one interesting observation is that in Eagle Creek, Riverside to a level, we've seen landslides occur in recent years, years after the fire. So in Eagle Creek in particular. This suggests that there's something changing over time, and particularly if shallow landslides tend to be the control. The timing of the debris flows in the case of Eagle Creek is kind of similar to the landsliding rates we see following timber harvest, for example, when there's no revegetation, about 3 to 5 years after. And that suggests that one of those evolving controls might be decreasing root strength. So here we are, testing root strength with what's called an Instron machine. It has a load cell. It gives us a load displacement response. We can measure tortuosity of roots. We can measure its stiffness. We can break really big roots. So here's an example of what root displacement looks like. And one thing we're planning to look at is when roots are dead, how much more brittle are they than live roots? This actually might be a control on how the strength of roots is immobilized and to what level it actually plays a role in this delayed landslide occurrence. We can break big roots. Most of the research that's looked at roots has looked at roots up to 7 millimeters. And I wasn't sure why until we actually tried to break a root that was 7 millimeters. You basically need the 2 heaviest people you can find, and you have a tensile device that you hold, and one person pulls, one person stands still, and when the root breaks, you got a data point. So that means you can only go up to so much load. The nice thing here is we can break some pretty big roots, more than 7 millimeters. Here's a root with about 20 millimeters diameter. And we can constrain the temporal decrease in root strength, as we've gotten this from several wildfire sites that occurred at different times. All right, quiz. How much load do you think it takes to break a 20 millimeter root that's less than 1 inch in diameter? Think about it. I wish I had the Jeopardy song. About 600 pounds. It's no joke. It takes a lot of loading to break these roots, and they're out there. So we plot the data up. There's scatter. They're always going to be scatter. But we see some things we expect. On the x-axis, diameter of the root. On the y-axis is the strength it takes to break it in tension, in kilograms force. Pardon the log scale, but there's some big and small numbers in here. There's 3 data sets so far, and we actually have to add 2 more, another one from Holiday Farm and one from Cedar Creek. But we have live roots, dead roots from Holiday Farm, Eagle Creek, and you can see the colors here. I've also plotted up kind of the classical relationships that give us kind of the general observed strength properties of Douglas fir roots from the literature. So you can see there's scatter, but we see that root strength increases with diameter, as you'd expect. Okay, cool. And we see that it quickly diminishes over time. If you plot up with a linear scale, you can see that just 2 years after a fire, we see that you can lose up to 50 to 70% of that root strength. There's a pretty significant drop, especially for the bigger roots. I talked to a root geek in my department. He suggested that some of this might owe to the different decomposition mechanisms for larger roots, which tend to be woodier. You can plot this up, basically looking at time after wildfire. So this is proportional root strength to a live root versus root diameter. We see 2 years after fire, there's quite a big drop, and especially for the big roots. And 5 years after fire, you might see as much as a 90% decrease in the root strength. We've compared this to some of the relationships for post-timber harvest, clear-cut, root decay, and we see that generally we see the same trend. They're in the same ballpark, which suggests that perhaps, some of those relationships are useful to actually quantify that loss of strength. Root size distributions, I think we need more data. Generally, we saw less roots in burned environments and less big roots, which is one that is a bit of a head scratcher. It's possible those roots smolder and disappear, but I think we need more data to actually see if that's the case. So far, we have about 200 root samples with another 150 on the way. Modeling, and I'll be quick here because I'm running out of time. We're only starting the modeling, but the idea is to basically look at 2 different controls here. One being the landslides as an initiation mechanism. The other being the sediment availability within some of these channels here. One being the fuel, the sediment, the other being the fire, particularly for debris flows that can bulk and grow after even a small, tiny, shallow landslide with small volume grows into something big. We're aiming to develop some models for susceptibility to evaluate both of these. Real quick, if we just took an example of our root strength and a simple slope stability model, and we used our hollow slope angle, the pore pressures, the water pressures we saw at one of our sites, and we use that root strength and density over time, we can plug it in for a simple slope stability model where we have factor of safety, which says how stable is a slope. The higher, the better, the more stable. We see that over time, we eventually reach a factor of safety of 1, aka instability, about 3.5 years for the data we have. There's a lot of variability here, but effectively it suggests this may indeed be a very strong control on the delayed landsliding we see. We're also trying to develop some kind of sediment transport models. This is really in the initial stages to kind of get an idea of the potential for bulking given a shallow landslide. And what starts today is actually looking at mapping. We've collected another aerial LiDAR data set for part of the Eagle Creek burn, and our idea is to difference the 2009 data set. U of O collected a data set from NCOM in 2018, just after the fire. There's a 2021 collection, and then 2022. Difference these and map them and analyze them to see what are the processes, what is the frequency of landsliding, how is bulking changing, erosion, all this. And this, real quick, is just some of the areas we've collected the LiDAR and some of the assignments we have for our mapping exercise that starts this afternoon. So with that said, we're still trying to constrain these controls. This project is just getting off the ground. So this is a work in progress, and we welcome any sort of expertise or input on what we observe. The site monitoring is the first step. We plan to get more out there, but it allows us to at least corroborate what we see in terms of climatic controls. We suspect that some of these delayed failures that we see, particularly from the gorge, are infiltration-driven. That is, driven by shallow landslides. Root strength may be a control in these burned, non-revegetated areas, may be a control on that multi-year lag between burn and debris flows. And of course, we're trying to look at modeling, bulking, and erosion, all those things. Eventually, we also welcome any sort of inventory information. And the most important thing is, of course, we always need more data. I always welcome more perspectives. I'd welcome anybody here to come and chat, to just join us. Share what you have, share what we have, just an opportunity to really kind of work on this together. We only have some narrow set of perspectives on the geo side, but I'd welcome anybody's thoughts and help as we pursue this project and gather more data. So with that said, I have to run to a defense after the break. I hope to chat with some people, but if you need to contact me, I'm happy to have coffee, my treat, or a Zoom call, whatever it is, just to chat about how we can get you involved. With that said, thanks for your time. Sorry, went over time.
Yeah, great talk.
Thanks. Thank you.
I drive through the gorge a lot, and I was looking up going, I wonder when the next Bridge of the Gods slide. Are there other drainages that have not failed that are similar to Eagle Creek that you guys are considering studying that have burned and potentially would act as sort of a reference for your locations?
You mean up in the gorge itself?
Gorge itself.
Yeah. That's a great question. At this point, we're only monitoring sites within the Eagle Creek burn, and what we have tried to do, what we're hoping to do is install another station there in an unburned location to at least have a reference. Finding a catchment that's similar, that's a challenge in itself. There's no way to drive to some of these sites. We had to hike in everything. But I would actually love to do that. And yeah, I'm with you on driving through the gorge and thinking about where the next big one's going to happen. In fact, you'll hear this afternoon, probably from Michael, a little bit about some of the slow movers they have in that area, at least one of them in particular. But we've placed our sensors near that one. But I'd love to. Thank you.
We have time for one more question.
Oh, please, yeah.
Yeah, good morning, and thank you.
Thank you.
To you and also the folks who put this on. I'm a fish biologist. I study the effects of fire on fish, and everything ends up in the stream, as you know, and so understanding better about these debris flows and soil types is just so important to me. And so I wanted to ask you a question about the root strength. Anybody who's ever tried to pull up a stump understands how strong those roots can be.
Yeah.
But what I'm curious is if you saw any, or if you were able to study the difference between like a younger tree's root strength versus an older tree's root strength, and whether or not younger trees, that if a burned hill slope that was losing the strength of the dead trees, if there was a lot of younger trees there, if that might help kind of compensate, if
Sure.
you will, for the loss of the root strength of the dead trees.
What a fantastic question. I appreciate that. So in that, one thing we have been looking at is actually the diameter of the trees, which, is associated with age, but of course growing conditions as well. There has been some research, naturally, looking at this and say the timber harvest aspect about when to replant, right? And in fact, that's part of why replanting occurs, within 2 years and all that. So what they have seen is that there is this kind of sweet spot where we see shallow landslides as a function of when you actually replant trees and everything like that. We haven't looked at it in the case of wildfire. And actually it suggests that maybe at some of these sites where, there is replanting, there's certainly some valuable opportunities to dig some more holes and break some more roots, particularly where we have, seedlings or younger trees, to kind of understand, well, are there differences in the actual strength or the stiffness? And how do those changes manifest over time, right? What's the weak point? And maybe is that a control on sediment yields? So I love it. It's been done in the post-timber harvest era, but not for wildfire. Great question. Thanks. Thank you, everybody.